Hi, everybody. Welcome back. So we're going to do, this is the second part of our lecture on adding predictors and interactions in multi-level models. I'll be talking about interactions. I'm going to spend a good bit of time talking about them in regression. Some of this may be a bit of a review, and you'll see why. It's because they're basically the same in a multi-level model. So when we talk about interactions, we're talking about, another way to term this is moderation, moderators. We talked about these in SEM a few weeks ago. So where we've got some focal predictor X, X is predicting Y, and the strength of that XY relationship depends on some moderator variable that I'm going to call Z. So in our simplest model in regression, we have three variables, an outcome variable Y, our focal predictor X, and a moderator Z. And so a moderator is a predictor that potentially predicts that X to Y slope. And when we fit this model in regression, we fit a model something like this here, where Y hat, our predicted value of Y, is equal to some intercept plus the slope of a focal predictor, plus the slope of a moderator, plus a slope that is the focal predictor times the moderator. So another way to say that is the slope of X, Z, and XZ. And this focal predictor times the moderator is literally where we multiply together values for every individual, multiply together the value of the focal predictor and the value of the moderator. Just multiply those together for everyone. That slope, here we've got B3, we test if that's different from 0, that gives us the test of the interaction. One quick note, and I think I might mention it later too, but just as a quick note, that these slopes, B1 and B2, these are not main effects. These no longer represent the effect of X and Z, they are conditional. Specifically B1 here, this slope represents the slope of X when Z is 0. B2 represents the slope of Z when X is 0, which is not the same thing as just the slopes overall. If you want to get what is just the effect of X and Z, you'd fit a model without that interaction term, without that product term in it, just fit a separate model. Okay, so we test if B3 is different from 0, and we use all our favorite software to do that, R, SPSS, SAS, whatever we like, and with regression, and we find that it is different from 0. So then we're left with, well, what does this mean? Okay, well, technically that slope of the product, B3 here, represents for a 1 unit change in the moderator, what is the change in the slope of the focal predictor? But interpreting that is, difficult to impossible to makes no sense. So instead, what we want to do is we often want to estimate what we call simple slopes. And the idea behind this is we rearrange our regression equation. So we take this regression equation here with these slopes and we rearrange it into two separate terms that are functions of Z. So first, what we call a simple intercept, the overall intercept, and the slope of the moderator. The second, the simple slope, the slope of X, and the product term X times Z, and we factor in X out here. And so what we have now is for any value of Z, for any specific value of Z, we can plug in a value of Z and compute an intercept and a slope. And so usually we choose a few conditional values of the moderator, look at the simple slope of Y on X for those values. So standard choices are the mean plus or minus 1 standard deviation. Whether those are good or not is sort of an open question. If you've got a pretty normally distributed variable, it works okay. If not, you might want to use the 25th and 75th percentile in the median or something like that of the moderator. But we pick specific values of the moderator, plug them in, and get estimates of an intercept and slope. And we know what the interaction is telling us is that the simple slopes are different. By definition, if you have an interaction, the simple slopes are different. So what we're saying is, well, we know the simple slopes are different. Now, what are those simple slopes for some key values of the moderator we're interested in? So let's say we're interested in a case where does group size, so the size of a group individuals are tested, moderate the relationship between language test performance and verbal IQ. So we've got verbal IQ is our predictor, language test performance is the outcome, and group size is our moderator. So group size ranges from 5 to 37, the mean is 23, standard deviation is 7.29. And so what we can do is if we plug in, say, the mean, 23 here, we could also plug in, 1 standard deviation below the mean, 1 standard deviation above the mean, and get simple slopes, assuming we know the slopes B0, 1, 2, and 3. So we can do this. We can graphically present those in the interaction with those simple slopes, what we call plotting. But we might want to know more. We can also do what's called probing. So probing is exploring magnitude and significance of the relationship between X and Y at different conditional values. Another way to say it is probing is testing, is that simple slope different from 0? And I think it's really important for me to point out, Probing an interaction is not testing if the simple slopes are different from one another. That's what our test of the interaction tells us already. In probing, instead, we say, are these simple slopes different from 0? It is entirely possible to have a significant interaction where all the simple slopes are different from 0. It's possible to have one where none of the simple slopes are different from 0. This is just another way to help interpret and give us more information. What we might want to know is the relationship between language test score and verbal IQ, is that significantly different from 0 in groups of 30? Or say, what about groups of 60? We test our simple slopes using a wald test, which is parameter estimate over the standard error. And so our parameter estimate is our simple slope here, b1 plus b3 times z. So for every different value of z, we have a different parameter estimate. And the standard error is this value down here. So this s squared this is the variance of b1. This is the covariance of b1 and b3, the coefficients, times z, and this is the variance of b3 times z squared. And one important thing is this standard error actually depends on the value of z as well. To find those S terms, we use what's called the asymptotic covariance matrix. To do that in R, we use the vcov command, and we'll see this when I go through and look at our software example in a separate video. I'll show you all of this. So in our example, the slope of x, the slope of verbal IQ was 3.346. The slope of the interaction was negative 0.31. So here we're computing it for, in this case, I'm going to do it for the minimum, median, and maximum group size. So here our simple slopes are 3.19, 2.63, 2.19. So we can see as group size increases, the effect of verbal IQ on language test performance gets smaller. The numerator here are the simple slopes with verbal IQ predicting language tests. And so they're all getting smaller. For our t statistics in the denominator, we're computing our standard errors for all of them. And so what we see is the standard errors are actually different, again, depending on that value of z. But all of these are all t statistics. They're all way bigger than anything we'd expect to see. They're all significantly different from 0. So this is a case where we have simple slopes that are all different from 0. They're all significant. So the significance of the simple slopes isn't as useful as how that simple slope is changing. So just to recap what you do in a simple slopes analysis, fit your regression model. If you have a significant interaction, choose the conditional values of the moderator, find the simple slopes and intercepts associated with each of those conditional values, plot them, probe them, and interpret. The problem with this is those conditional values are pretty arbitrary. Using the minimum, the median, and the maximum, or the 25th, 50th, and 75th percentiles, or the mean plus or minus 1 standard deviation. These are all really arbitrary. If you have a moderator where there are specific values that are meaningful, so if you have a moderator where there are specific values that represent mild, moderate, and severe levels of depression for your moderator, okay, use those. That's great. Most of the time in behavioral science, though, we don't have those specific values of our moderator, and so we might want to pick something else. So what we could do is we could use what's called a JN technique, or region of significance. And this turns around our question. Previously, we were saying, okay, I want to know for this value of the moderator, is the simple slope significant? And now we're going to say instead of is the simple slope significant for a specific value of the moderator, for what value is the moderator? What value is the moderator give us a significant simple slope? So what we do is we start with our t formula to get our t statistic for the simple slope. And instead of plugging in a value of z and solving for t, because everything else is a constant that we know, instead we say, well, what if we plug in a value for t and solve for z? And this is not trivial. This is actually more difficult than it looks, but we can do it. And Johnson and Neiman worked this out. And what we get is a region of significance, because we're using a two-tailed test with two t-values. If we go back, we can see this is plus or minus. We're going to do it both for positive and negative 2.02. And so that gives us a region of significance, a range of values of the moderator, where it is either the case that between those two values of the moderator, the simple slopes are significant, or outside of those values of the moderator, the simple slopes are significant. So just as a quick example of a Johnson-Neiman technique, here is our R code, and we'll see this worked out in a little more detail, but here is our R code for verbal IQ and group size and their interaction, predicting language test scores. The Johnson-Neiman technique says when group size is outside of the interval, so when group sizes are less than 75.29 or larger than 244, the slope of the slope is significant. P is less than 0.05. Well, given that the largest observed value is 37, what that's telling us is all the simple slopes are significant. And here we have simple slopes of that plus or minus 1 standard deviation as well. We can also plot these, and again, we'll see all these in the R example. Here's a plot of the simple slopes at plus or minus 1 standard deviation around the mean. There's that Johnson-Neiman technique again I mentioned. And then this plot, and I'll talk about this plot more. This is what we call a Johnson-Neiman plot, where now the x-axis is the values of the moderator. The dark line here is the observed values of the moderator, and the y-axis represents your simple slopes. And so this line here represents how simple slopes change across values of the moderator. And these bands here, these sort of curved bands, these are what we call confidence bands. So the idea is this is at any given value of the moderator, the line at that point represents the simple slope, and those bands represent a 95% confidence interval. And as long as 0 is not between those bands, the simple slope is significant. So here, all the values we observe are significant, so they're all blue. I'll play with this plot a little bit when we do this in R, and I'll show you some of the different ways we can look at it. So what about multi-level models? Well, multi-level models, things are theoretically a little more complex. We can have random slopes. We can have our predictors in different ways. So we could have 2 level 1 predictors interacting. So this first case we see here, where we've got x1 and x2 and their interaction. 2 level 2 predictors interacting to predict the intercept. W1, W2 interacting, or a level 1 to level 2 predictor interacting. So we've got xij and wj and those 2 interacting. And one of the things I want to point out is that you'll notice I only gave you the reduced form equations. And I did that very much on purpose. If you look at the level 1 and level 2 equations, these all look like different and somewhat scary things. If you look at the reduced form equation, it's very easy to see these are all basically the same model. What's changing is our interpretation, right? And with 2 level 1 predictors, our interpretation is, the moderator affects the relationship between these 2 values, and it's all in the individual level. Level 2 predictors, all our interpretation is more at level 2. And for this cross-level interaction, the trick with that is that in a cross-level interaction, so in the other 2 models, I'll say, which variable is the focal predictor and which variable is the moderator is really up to you. In a cross-level interaction, it makes much more sense that the level 2 variable is our moderator and our level 1 variable is our predictor. And that's the way we usually set those up. In this case, all of these are random intercept only. You can add random slopes to any of these for any level 1 variable. It does not change plotting and probing. It does not change testing. You just do what is appropriate. Plotting and probing interactions only uses our fixed effects. So how do we do interactions in MLM? Exactly the same way as regression. We compute product terms, product of x and z. We include those in our predictor, our simple slopes. We test them the same way, reasons of significance the same way. We only use the fixed portion of the model, which is interpreted like regression. The only difference is in understanding our interpretation and where to fetch the asymptotic covariance matrix. And it turns out we don't even need the to find the asymptotic covariance matrix in R anymore. So there are calculators at quantsci.org for finding some of these. I'm not going to talk about those because there's also a package in R called the Interactions package that automates a lot of this with Elmer objects, and we'll see examples of that when we do this in R. So just a couple of notes here at the end. Dichotomous moderators. If your moderator is dichotomous, that's cool. Just use a dummy variable to represent z. So 0, 1, it's usually best if it's 0, 1 coded. So interpreting results, we would only interpret results for the observed values. So basically, this is a case where we would not use our Johnson-Neiman region of significance for the dichotomous moderator. We would just look at the simple slopes at the specific values of z. What about centering? What about centering when adding interactions? Short version, don't do it. Longer version. So centering aids in interpretation technically. Because with an interaction, remember, those quote-unquote main effect slope, the slope of x and z, are interpreted when all the other variables are equal to 0. So when we mean center, we make those slopes represent, this is the slope of x when z at the mean of z. Now, whether that's useful, I don't know. I don't think it's terribly useful. I don't think it helps a lot. There are these old recommendations out there, and they're old. that say centering affects multicollinearity, you have to do it to correctly estimate your interaction. Those are completely wrong. There have been article after article after article written about these. There's one called Centering, the title is literally Centering does nothing to reduce multicollinearity in moderated multiple regression. So don't do it. Don't bother centering. It doesn't buy you anything. Now, the caveat to that is in multiple modeling, there are multiple ways of centering. So here I'm talking about grand mean centering, but there are some other ways. You'll hear people talk about group mean centering. That has some other implications that actually changes the model you're fitting. And that does not necessarily happen here, but that also is not something that people discuss when they talk about centering and interactions. What about higher order interactions, three-way, four-way interactions? Sure, you can do it as long as you include a product term for, say, all three variables and all the lower order terms. So all three, for a three-way interaction, all three quote-unquote main effects, X, Z, and W, all three two-way interactions, XW, XZ, WZ, and the three-way interaction. And again, your interpretation is limited to that higher order terms. You can have any combination of predictor levels, 1, 1, 1, 2, 1, 1, 2, 2, 1, 2, 2, 2. And so you have, for simple slopes, then you find simple slopes at conditional values of 2 moderators. So the interactions package has this as well. So that's it right now. One of the things I want to mention is this is usually the time in the semester where we have extra time to talk about projects. I'm gonna post some information about projects, I think, on Thursday or Friday of this week, talk about them, talk about what I'm expecting them to look like and how we're going to do them in the class this semester. So I will talk to you then. Be on the lookout for software examples as well.